Okay, let's get started. Welcome everybody to the second webinar in this series related to EASY, the European Environment for Scientific Software Installations. Today we'll give an introduction to CernVM-FS, and don't forget to also consider joining the future or the upcoming webinars, one on EASY Build, one on EASY for CI/CD, and one on using EASY as the base for a system stack. So a central software stack. You can still register for those, so if you're interested, please do. The link is here on the slide. You can scan the QR code, or you can just click the link that was in the email that was sent to you. So we'll get started with today's session, an introduction to CernVM-FS, which will be presented both by myself and Valentin from CERN. I'll quickly give an overview of the agenda. So we'll really start from scratch, explaining you what CernVM-FS is. We'll very briefly cover EASY as well, because we'll be using that throughout the webinar as an example of a CernVM-FS repository. And we'll do that very hands-on. We'll install and configure the CernVM-FS client software to get access to a repository like EASY. Also look into using CernVM-FS on large-scale systems, setting up a proxy and a Stratum 1 hands-on, and explaining why that is necessary. We'll look at alternative access mechanisms in case the recommended approach is not possible for some reason. And then look into monitoring and troubleshooting CernVM-FS. We'll very briefly cover how to create your own CernVM-FS repository. And at the end, we'll look at software startup performance and why that's a very relevant aspect when talking about CernVM-FS. I'll pass the microphone to Valentin to get started with the first part of that.
Yeah, thank you, Kenneth. Thanks very much for the introduction. So I'm Valentin. I'm the lead developer of CVM-FS at CERN. We have a small but dedicated core development team here. And besides myself, there's also George and Seem connected in this meeting today. And so I want to get started by actually talking a bit about the motivation, what we're trying to do with CVM-FS, because it's kind of like a bit of an unusual idea if you've never heard of it. But it's basically motivated that we're in a particular situation with scientific computing. I hope this doesn't come as a shock to you, but if you were to actually just try to run your jobs from containers, for example, studies have shown that on average, you're actually using between 15 and 20% of a container image for a job, actually. So the rest of it you're going to download, but you're never actually going to read and use the files. Of course, you can minimize aggressively your container images, and that is going to help, but that's kind of a lot of effort. Especially for scientific software, where you might have really a data center full of nodes waiting to get started on a particular simulation job, as it's in particular the case for high energy physics, for which CVM-FS was invented. And there are, of course, the more traditional package managers on Linux, RPM, dpackage, apt, and the other suspects, but is a bit of a different problem and kind of hard to scale up to a really distributed environment. And so for actually a data center that tries to run workloads in a distributed environment, really it turns into a distributed denial of service attack on the file system that actually provides your software, or the server where you download your packages on. And this is a very metadata heavy access. So if you actually when you run software, now you have to resolve all of the dynamic linking, and you look for shared libraries in a lot of search paths, and all of this becomes a very tricky problem. And in the early days, also at CERN, we tried to use general shared file systems, networked file systems for this task, and this really didn't work out well. And so one of the solutions that we came up with for this problem is the CernVM file system, CVM-FS. And so what is the idea behind this? is basically that you have a global read-only file system for software distribution that has a user experience that's very similar to an on-demand streaming service, but for scientific software. So the idea is then really, if this software is actually going to change quite a lot, and you have to really read only parts of it, as it's the case for high energy physics software stacks, really, why not make it really on demand, and only download the files that you need when you need them. So you can see here in this console text box a bit how this is going to look like. So if you access CVM-FS, you're actually going to mount the CVM-FS file system as you access it. If you have AutoFS enabled here, and then as you access it, actually you're going to get the metadata, but you're not actually going to download the files yet. Only if you actually read the files, as I do here with cut, we do a just-in-time download, and then you're going to actually download this README file from the easy repository here, as the example shows. Just to talk a bit more about the technical background and implementation. So this is implemented as a file system in user space with libfuse. This makes it very flexible. And over the years, by now, CVM-FS is quite a mature software project, so it's over 10 years old. There's a lot of technical improvements that have gone into making this work very well. So basically, we can deduplicate the files that we store on the backend. And the files from the backend are always fetched via plain HTTP transport, which allows us to cache the files at various levels, which actually makes then CVM-FS actually performant. So we're going to actually see a bit later how this whole infrastructure and architecture is going to look like and how to properly set it up. We also compress the data, which makes this whole thing really quite efficient at archiving and keeping all data around. And one of the side effects of this is that at CERN, CVM-FS is also a great archive for software preservation. And then finally, we can also ensure that the client really gets the files that are actually being sent from the server. So we do some verification of the data integrity here as well. All right. Just one more glance behind the scenes of CVM-FS here. So how do these file systems in user space work? Basically, so we implement basically all of the necessary system calls that are being done on /CVM-FS. So if you do an ls, that's actually going to be a reader that is going to go to the kernel, and for a fuse file system is actually going to ask the CVM-FS process. If you install CVM-FS, it's going to run a CVM-FS process that's responsible for the mount point. And that's going to then implement all of these syscalls only for the read-only part, as we're not like a writable file system. The writable part is going to be done by the server tools, which we're going to talk about. But basically what's then going to happen behind the scene is that if the file is there already in the local cache, we basically just use that file and going to return that file, and it looks to you like it's there on /CVM-FS. If it's not yet in the local cache, we first download it from our object store from the server, place it in the local cache, and then proceed as in point 2. And that's the basic idea, and this is going to allow us to basically do all of this on-demand reading of files. So originally, CVM-FS was developed for a particular type of infrastructure that is the computing grid. And this is basically the main computing resource for the Large Hadron Collider, the biggest experiment at CERN. And the naming should evoke a bit this idea that you can very flexibly just plug into to this computing grid your compute workloads as you could plug into the electrical grid whatever device you have. And you can see that this is quite a big infrastructure. And the idea that also the software is basically just available on all of these very different sites that are distributed all over the world is, I think, is a very powerful concept. And also, if that actually sounds familiar with Euro HPC and this federation that are being done at supercomputing sites in Europe, I think is a very similar and very nice idea of how to get a uniform computing access to very varied resources. All right. So to summarize, basically, what we try to replace, basically, we replace this access of software from a lot of nodes that are currently trying to start up a job with this really distributed architecture. And you can see that there are several layers. Kenneth is going to show this a bit in more detail. And basically, what we then try to do is have is to distribute all of this data and have an efficient cache and proxies on the way between the client and actually the source of the data, which is the stratum 0. And that actually makes this work in a distributed environment as we had before. All right, just to give you some numbers for the CVM-FS deployment at CERN. Here we have about 15 Stratum 1s. These are basically the sites that have a full copy of the repository data for all of the software repositories. We have about 260 of those. You can see here that there's a couple of very big ones, in particular for the LHC, for the big LHC experiments. But then there's a lot of smaller ones as well, in particular also from astronomy, for LSST, and for various other small experiments here as well. We have around, I think the latest number is 20 billion files in the /CVM-FS tree that you can publicly access. It goes to about 2 petabytes of data. This is actually compressed quite efficiently. So I think we're going to see this a little bit later on. But the actual size on disk is about 1 petabyte, I think. So this is quite a good compression ratio then in the end. So because actually our colleagues from CERN IT agreed for this tutorial here to let us show their production dashboards, which are normally not publicly accessible. They're not particularly sensitive, but for this tutorial, we can also show you today. Then at the end, basically a few of the numbers as CERN IT has deployed CVM-FS. All right. There's also the container images that are actually not so relevant for today if you're interested in easy, as you have your own quite clever way of providing isolation from the so that there's this compatibility layer that doesn't really require containerization of software. But just to mention that we actually do have a way of unpacking container images to CVM-FS and then using those from there. All right. And I think with that, I just give you a quick overview also of the CernVM-FS code. The important parts that I already mentioned is that we have a client that is actually installed on the worker nodes that allows you to access the repositories and get /CVM-FS and to start using your software from there. And then we have the server tools that actually allow you to manage, create, and maintain the repositories and then to publish software into those. And I think today also we're going to get like a hands-on view of how to actually run these. There's a few more utilities here. They deal also with particular situations on HPC sites where you might have constraints that make running CVM-FS a bit tricky. And we're going to take a closer look at those as well. So in particular, shrink wrap, which lets you take parts of CVM-FS offline. And then various extra tools sort of for monitoring, which we're going to then touch on later on as well. All right, and with this very brief overview, I'm going to now give back to Kenneth to show actually how CVM-FS, what CVM-FS is doing in easy for easy and how it integrates there in the project.
Yes, thank you very much, Valentin. So we'll speed run through easy a bit, just mainly for the people who are maybe not familiar with it yet. We had a webinar on this last week. The recording is available on on the page for the webinar series, so you can go and see an in-depth look into easy there. But just briefly, easy is the European environment for scientific software installations. So through CernVM-FS, we do on-demand streaming of scientific software installations that are optimized for specific generations of CPUs, mostly focusing on Intel and AMD, so x86 64-bit CPUs, but also ARM CPUs. I'm already looking ahead towards the upcoming RISC-V CPUs as well. And the way we build these software installations are such that they work on any Linux distribution. So we don't care whether you're using Fedora or Ubuntu or Rocky Linux or Debian on your clusters. We give you binaries that work on all of these. So it really becomes a uniform software stack across the whole range of systems. You can use easy on your laptop and on HPC clusters in cloud virtual machines and so on. And we also are very community oriented. So we want to tackle these challenges that we see with building a software stack like this together with you. So we're also open to contributions in various ways. This is the structure, the design, let's say, of easy, where we have a file system layer, which is essentially just CernVM-FS, mainly how we distribute the software. We have a compatibility layer in between, which is a small Linux file system hierarchy that provides a couple of libraries, including glibc, for example. This is how we shield ourselves away from host operating systems like Fedora or Ubuntu. And on top, we have the actual scientific applications and all of their dependencies. And when we build these, we make sure they link to libraries in the compatibility layer so that you're not relying on libraries from the host. And that way we can give you binaries that work on any Linux distribution. And we actually don't do this once, but we do this several times for different generations and different families of CPUs. We test the whole stack as well with Reframe. So everything here is really open source software that we use for specific purposes. And by combining all of those, we build something bigger that becomes very interesting to use. So this is a same thing, but a bit of a different look. So we rely on CernVM-FS for streaming, for on-demand streaming of software installations. We rely on the compatibility layer to become independent of the host operating system. We sometimes call this containers without the containing. So there's no container runtime involved, but we do pull similar tricks as are used in container images. And then we optimize the software installations we have on top of that for specific generations of CPUs and also different types of GPUs as well. Today, mainly NVIDIA GPUs, but we're also looking into AMD GPUs actively as well. We also do auto detection of what CPU and GPU you have, and that will show up in the quick demo. You don't have to tell or you don't have to find your way around in the repository yourself. You can just source an initialization script, and it figures out what it needs to know to give you the best possible binaries for the software that you want to use automatically. So what we're going for with this is to build a shared software stack for a whole range of systems. To some extent, we focus on the Euro HPC infrastructure, so the big European supercomputers. But as a consequence of that, we actually support a whole range of systems, definitely smaller HPC clusters within Europe and way beyond that as well. And also on your laptop or in cloud virtual machines, it all works nicely because of the way we build things. So we essentially install software once in easy. And then as long as easy is accessible on a system, those software installations can be used there. So it becomes maybe a bit more effort to get something installed, but once it's installed, it can be used anywhere. We also have a workflow for adding software to easy, which is semi-automatic, well, as much automated as makes sense. So we don't manually install additional software into easy, but we have bots in place and scripts in place that automate that process as much as possible. We have various checks along the way, either by human reviewers who look into pull requests or automated test suites that verify that everything is working as it should. We also sign our tarballs before we actually ingest them in the easy CernVM-FS repository, so we make sure there's no shenanigans going on along the way. And this also enables you to add your own software, or at least propose specific software to be added into easy without you giving us some binaries that come from God knows where. So we build everything from source, and that way we have full control over what goes into easy. And the user experience here is, like I mentioned, there's a script. I'll actually show this hands-on in a bit. A script that you can source in the software easy.io repository under /CVM-FS. Once you do that, it will detect what type of CPU you have. It will prepare your environment for using the software that we have in easy. And from that point forward, you can start loading modules, loading environment modules for specific software like Bromax, and then just start running the binary. And in the background, once you launch this binary, CernVM-FS will actually notice, oh, I don't have this binary yet. It will go ahead and download it. It will also download all the libraries that are necessary to run this. And as soon as it has provided everything that's necessary, that binary can launch. And this is done fully transparently. So as an end user, the first time you do this, you maybe notice a small delay, and we'll look into that at the end of the webinar. So that software startup performance aspect. But once it launches, everything just works nicely, and it looks and feels just as if the software is installed locally on that system. And this is the process that Valentin already explained. So CernVM-FS will first look into its cache. If that cache is not having the data that is necessary, it will pull it from the mirror server and the CernVM-FS Stratum 1. First put it in the cache and then launch the binary. And the mirror server is fed through a central server. That's where we actually add software into. So all of this will become more clear, I hope, through the hands-on demos that we do. All right, so that was very quickly about easy. So easy is going to be our main example CernVM-FS repository. So let's start with trying to get access to it. So to access a CernVM-FS repository, you need to essentially do two things. At least in the recommended setup, you need to install the CernVM-FS client software. So that's a small package that you install with Yum or DNF or any of these standard tools. And once that's done, you also need to configure it so it knows about the CernVM-FS repository that you want to use. So which servers does it need to talk to get the data that's included in those repositories. And also how much disk space, so how much resources can it use on that particular client, on that particular system for its client cache, for example. And then some details about connectivity, and there's a whole bunch of options that you can set. So when you access software in this particular repository, you'll actually talking to CernVM-FS, or at least the Linux kernel is passing those system calls to CernVM-FS. And that way you're getting access to the software, even though that's being pulled in remote. That's done all transparently to the end user. So I'll quickly show you what needs to happen, and then I'll actually do it hands-on as well, just so you can see how quick it is to get access to the CernVM-FS repository. So first step is installing the client software. For this, pre-built packages are available from the CernVM-FS website. For different Linux distributions, different CPU families, so x86 and ARM, and there's packages for Mac OS as well, if you want to try it there. On a RHEL-based operating system, so something like Rockwell Linux or Red Hat Enterprise Linux, it boils down to downloading an RPM for CernVM-FS. In this case, where the first step here is installing the release package, the CVM-FS release package, which adds the repository where you can get the RPMs for CernVM-FS itself. So this DNF install will add the repository as a known repository. And then we can install the CVM-FS package itself. So this is the client software for CernVM-FS. And then once we complete the setup with the CVM-FS config setup, we can actually straight away start accessing CVM-FS repositories. So step 2 is then configuring CernVM-FS to access the repositories. Now, actually, CernVM-FS comes out of the box with a sort of special repository, the CernVM-FS config repository, that's accessible after installing the client software. And this repository is responsible for giving configurations for other repositories. So straight out of the box, you have repositories that you can use and which give you the necessary configuration and information to access other repositories. So Easy, for example, is part of this default distribution of repositories. And you can see that as soon as the client software is installed, you can check which files are available in the CVM-FS config.cern.ch repository. And you'll find a configuration file there for easy.io, so the domain for Easy, and also the public key that's connected to those Easy repositories. So that's one way. If your repository is well known or part of the flagship repositories, you're good to start straight away. If not, it's not that difficult to get access to the repositories that you know about. You need to do two things, really. You need to tell the CernVM-FS client software about the Stratum 1 servers. So where can it get the data for those repositories? It needs host names or IP addresses. And then it also needs a public key because that's the information it uses to verify that the data that it gets is genuine and hasn't been tampered with along the way. And that goes into etc CVM-FS keys. In the case of Easy, we actually provide a package in RPM that we create ourselves, CVM-FS config Easy. If you install this, it actually gives you the configuration file and the public key as well. And in this case, it's just installed locally in etc CVM-FS. It's not coming from the configuration repository. Now, there are reasons to not rely on the configuration repository, although that does come with significant benefits. If we update something in there, you will automatically get those updates without having to do anything. If you install this package yourself, you need to make sure that if there are updates, that you also install those updates to get the new information. But by relying on local files, you get the flexibility to maybe change things in here if you want to, or to make sure that everything isn't moving or isn't being changed behind the covers on a live system. So you have, to some extent, more control over the configuration when you install it under etc CVM-FS. And then after providing access to a repository or providing the details to access that repository, there's a bit of additional configuration you can do or should do. For example, if you want to use a proxy server for accessing the Stratum 1 mirror servers, or if you have your own Stratum 1 mirror server, which we'll go through actually in this webinar, you can configure it under etc CVM-FS as well. You can also tell how much disk space the client cache can use. In this case here, this 10,000 indicates that CernVM-FS should not use more than 10 gigabytes of disk space for managing its client cache. And also the location of that client cache, which is by default for lib CVM-FS, you can change to something else with the cache base setting here, for example. These are just 3 examples. There's several more configuration options that are available and that are well covered in the CVM-FS documentation. So let's actually do this hands-on. I'll jump to a terminal here, and I have a small Linux system prepared, which is fired up this morning. So it's only been up and running for about 3 hours now. Now, the unfortunate thing is this doesn't have a lot of software. It has a relatively old Python 3 version. It doesn't have the module system at all. So the module command, the lmod package is not installed. So this is a system with, 8 cores and some memory, but there's not much to do here yet because we don't have any scientific software available. So to get access to Easy, and I'll use our documentation, it's actually sufficient to install CVM-FS. And since we're on a RHEL-based system, that really boils down to doing a yum install or a DNF install of CVM-FS. I will also install the configuration for Easy by downloading this additional RPM and installing it, the CVM-FS config Easy RPM. I'll complete the setup with the minimal amount of local configuration, so setting up that 10 gigabytes of disk space for the client cache and then complete the setup. I'll just copy paste this here and run it and show you how quickly we get access to Easy. So this should only take about half a minute or so. It will start with downloading the CVM-FS package and all of its dependencies. And here you can already see, this is a bit of a spoiler, we're working on an ARM system actually here, so it's not an Intel or AMD system, but it's a system with an ARM CPU. So once it has the repository for CVM-FS, it can install CVM-FS itself and all of its dependencies. It will then download one more RPM for installing the configuration for the easy repositories. Right, so there it goes. It installs that as well, and then we're done. So now I can start checking what we have on the CVM-FS. This looks like it's empty, but it works a bit similar to websites. If you know the website exists and you use the right URL, in this case, if you use the right repository name, you can check its contents, and then things are working, and the repository actually gets auto-mounted. So in this case, we have access to software easy IO, and the config repository also popped up because that was poked in some sense by CVM-FS. And once it's available, in the case of easy at least, we can source that init script. It will detect what type of CPU we have. In ARM Neoverse V1 CPU, it will not find any GPUs in this case. And then after doing that, we can start running software like Chromax, for example, which is coming from /CVM-FS software easy IO. I won't actually run anything here, just getting access to it and setting up that initialization script or running that should be sufficient to convince you that we actually have access and everything is working as it should. So you can see by just installing CVM-FS and doing some very minimal configuration, that's enough to get access to one CVM-FS repository like easy, and actually a whole bunch as well, as long as the configurations are known. So it's a very low effort thing. Now that was very easy because this is just a single client, of course. If we're talking about multiple clients and potentially hundreds or even thousands of clients, even within a single HPC cluster, we can easily be talking about hundreds or thousands of servers, then things change quite a bit. Now, all of this data for easy specifically, or really for any CernVM-FS repository, is coming from the cloud in some sense. So servers, mirror servers on the internet that feed you the data as you need them. Now, of course, if you start doing that with thousands of systems all on a single site and then multiple sites all across the world, you're really hammering that network quite a bit. And you're also exposed to the network latencies and the bandwidth issues that come with that. So CernVM-FS was really designed from the very start to deal with this and to be very scalable. So let's unpack that a bit, what's going on in this cloud, in this middle part here. It really begins with the Stratum 0, so a central server where the repository was created and also where it's updated, so where software is being added into this repository. This one feeds mirror servers, Stratum 1 servers in CVM-FS speak. There's typical multiple of them, but not hundreds of them, more like a dozen is already quite a lot. So these are automatically synchronizing with that central server. So as soon as any software is being added in here or any data is being added to the repository, they will automatically synchronize and pick up the data as well. Then these are, although we have multiple ones, they're typically geographically distributed. So you don't want to be talking directly to only one of them because that hammers that server quite a bit again. So there's another layer of indirection in between called proxy servers. So these are attached or are synchronizing in some sense with mirror servers as well, but they don't have the full data. So they only have stuff that's been actually requested by clients, by users, and they only keep track or they only download from the mirror server what is actually being used. So these are partial caches to some extent, but they typically have, there's typically a bunch of them and they each operate independently. So one of them may be having copies of software that other ones don't, and that's all okay. Now, what really helps as well is that you have a setup like this locally, especially for big systems. You can have your own mirror server or maybe two with a failover kind of setup, and then proxy servers that offload that mirror server a little bit. So even if you have tens of thousands of worker nodes in your cluster, you can avoid hitting the network, the central network, and being exposed to those network latencies. You can keep all traffic essentially coming from the nodes local in your network to make sure it's fast and reliable. So mirror servers, Stratum1 servers, and proxy servers are important concepts when we're dealing with CVM-FS. So let's look at that a little bit more. When we're talking about proxy servers, these are essentially have a partial cache or a partial copy of the CVM-FS repository that are being used. As soon as clients use part of the repository running GROMACS, for example, they will talk to a proxy server that can then either feed the data directly or first get it from the mirror server and then feed it back to the node. So ideally, these proxy servers are close to the clients to help with the network latency, to help reduce that. And they're also there to offload the mirror server, so to make sure that these do not get hammered and then are slower in handling all the queries. This is usually done with a squid proxy, which is a particular implementation, but there are alternatives and maybe better alternatives available. Varnish is one of them. And then the mirror servers themselves, so these are the second layer of cache in some sense, or the third layer if you count the local client cache. So these have a full copy of the contents of particular repositories. So they are set up to mirror particular CernVM-FS repositories. These are typically close to the proxy servers, so they can feed them quickly with the data that they request to help reduce the network latency. And since they're a full copy, they also help with the network or an internet disconnect problem, either accidentally or deliberately. So as long as your network, your Stratum1 server is in your network, all traffic to the outside world then doesn't matter anymore. You can keep all traffic local within your network if that's important to you. These mirror servers sync periodically with the central server, with the Stratum0, and they do that for those selected repositories, and that's called replication of the contents of the repository. And to give some idea for the main easy repository, softwareeasy.io, today to set up your own mirror server, you would need about 360 gigabytes of disk space right now, and that's about growing with 1 gigabyte per day on average. So it's not insane in terms of resources that you need to run one of these mirror servers within your own network. Now that's for easy. For other repositories, and especially those at CERN, so Valentin showed some of those numbers, we're talking about a different scale there. So setting up a mirror server for a CERN repository is definitely a whole lot more demanding. So let's also look into this a bit more hands-on. So let's start with setting up our own proxy server. For this, we need to install Squid. So we'll use the Squid proxy server here and configure it a bit, and then actually start the Squid service. And then we'll need to change something in our client configuration as well to make sure it's actually using that proxy server. So we need to set CVM-FS HTTP proxy as a configuration setting, and then reload the CernVM-FS client configuration to make sure it picks up on that setting. And this is how, oh yeah, I skipped a bit here. What's important for a proxy server is a couple of things. It needs fast disk because it will be serving lots of data, and you want to make sure that the disk that the data is coming from doesn't become the bottleneck. You really want the network to be the bottleneck in some sense. And of course, you need sufficient disk space. So something like 100 gigabytes for easy is already quite plenty, because we're talking a partial mirror here, a partial copy. Of course, you want a fast and reliable network connection to all of the clients, so all of the nodes that will be using or will be talking to this proxy server. And the port on which the proxy server is running, which is typically 3128, will have to be accessible to the clients, of course. So in terms of firewall and network ACLs, you need to make sure that's working correctly. The configuration file here is, of course, very specific to Squid, but to give you some idea, the important parts here is the ACLs, like the local nodes that are the IP range that are allowed to talk to this proxy. So you better make sure you protect your proxy server a little bit, that it doesn't get abused for proxying stuff you don't want to. You can also specify which servers it is proxying. And there you want to make sure that you're proxying the Stratum1 servers that are relevant for the repositories that you're interested in. In this case, the easy.science here is the domain that we use for the Stratum1 servers for easy. cern.ch and opensciencegrid.org are there mainly for the CernVM-FS config repository that we already saw. And then ports and some network specifications to make sure you only allow those and disallow everything else is important. And here you can also specify how much disk space the Squid proxy can use. In this case, we're telling it 100 gigabytes of space is all you have. And then some optimization settings for memory usage and so on. So some pretty relatively basic things, mostly network access and resources that are available to the Squid. All right, let's actually do this hands-on as well. So I'll SSH into another system here, which I have prepared a proxy. And this one doesn't have any CVM-FS things yet. It has no access to CernVM-FS repositories in any shape or form. And it actually doesn't need to, because CVM-FS does all of its traffic over standard HTTP. So in some sense, this is just a regular web proxy server that we will be installing. Now let's go ahead and do that. I'll jump to the tutorial section here and go to the proxy setup. So we're still updating this page a little bit. That's why you have that banner on top. But for what we're going to do, everything that's in here should be working. So we'll start with installing the Squid software from a standard RPM repository. And then we'll go ahead and set up the configuration. I'll copy this and just make a minor change to it to make sure things are working and hope that I don't make any mistakes along the way. So here this comes with an example configuration, but we'll actually wipe this whole thing and just go with a more minimal configuration. One thing I definitely want to change here is make sure this is a proxy for the easy Stratum 1 mirror servers. So I'll add .easy.science as a domain here. And here I want to make sure that the client that I'm using here is able to access that proxy server. So I'll copy its IP address and hopefully I don't mess that up. Let me double check that here as well to make sure that makes sense. Client 1 is, yes, that's its IP address. So that should be okay. And then after doing the configuration, I want to make sure this is actually parsing correctly, that I didn't make any silly mistakes, no error messages here, so that looks good. And then I'll go ahead and start the Squid service. So this is now running. I can check its status. This looks green and active. This looks all good. So the next step is then, go back to the slides. The next step is to reconfigure our client, our CernVM-FS client, to actually use that proxy. So I'll create or change SSH back into our client. And I don't have them yet, so I'll just use VI. It is a pretty minimal client system. I'll set up the proxy configuration, and here, of course, I'll use an IP address, not an example host name. So this should be the IP address of our proxy. So now I'm just telling CernVM-FS to use the proxy that we've created. And if I've done that correctly, after doing a reload, that should be working. So it now did actually a reload of the configuration, and let's actually check if that's worked. So with CVM-FS config stat, I can check how the connection is being made. It's currently not mounted, so I need to trigger a mount. And then see that, and you can see here that the connection it's making is, to one of the easy Stratum 1 servers. In this case, the one in AWS sitting in the EU somewhere. And it's doing that through a proxy that we've just created, and that's all working because it says online. So that means when I source this and actually load GROMACS, let's say, and then try to run the GROMACS binary, it will actually be working as it should. GMX version. So now it's pulling in that binary, pulling in the libraries that it needs, and it's actually able to run that binary. So that looks all good. So that was installing a proxy server of our own to make sure that if we need to download any data, any software from one of the public mirror servers sitting in the middle here, that we now have our own proxy server right next to our client, and that things will be faster from the second time onwards we run a software package. Okay. Now that's a proxy server. That's already very helpful, but maybe that's not good enough. Maybe we want to make sure we have a full mirror of the repository very close to us as well within our own network, just in case we're no longer able to access the internet or there's a network issue that we're not blocked from getting access to any of the software. If we want to do this, if we want to set up our own private Stratum 1 mirror server, then we need to have a separate setup, really, a separate system, which is maybe a bit bigger in terms of disk space, because here we'll at least for easy, we'll need at least 360 gigabytes of disk space, and this is growing every day. And we also want to make sure that mirror automatically synchronizes with the central server. So we need to make sure we have lots of room for growth here. So to get this started, once we have a virtual machine or the server prepared, we'll install the CVM-FS server package after adding the CVM-FS repository or the package of the repository of CVM-FS packages. Then we're able to install the CVM-FS server package, and we'll may need some add-ons. I forgot why this is necessary, but this is more related to monitoring, I think, or I'm not actually sure what this package is for, but it may be required. Similar to the proxy server, you want a server with a fast disk and a fast, reliable network connection to the proxies and the clients that you will be using, or actually only the proxies if the clients are only connecting through the proxy servers. And this is standard HTTP traffic, so it sort of looks like a web server. So just port 80 standard HTTP is all you need to make this a private Stratum 1 mirror server. So after installing the CVM-FS server package, and let me kick that off first so it can chew on that in the background. I'll start a new tab here, and I'll go to a Stratum 1 server, which doesn't have anything installed yet either. I'll start with copy pasting all of this, which should work. Let's make sure that does. Looks like okay. So I'll let it install that package and go through the next steps first. So the next steps here are then to make it aware of the easy repository that we want to mirror. That involves setting up some configuration, mainly making sure we have the public key for easy.io. And let's say, yeah, you need to copy this in the right place. It's CVM-FS keys and for the easy.io domain. In the case of a private Stratum 1, which is what we're doing here, it makes sense to disable the Geo API service that CVM-FS has. So it uses this to essentially announce where it's located geographically, and then clients or proxies can use that information to pick the closest Stratum 1 server. If you're setting up a private Stratum 1, which is only going to be used within your network, that doesn't make a whole lot of sense. So it makes sense to disable the Geo API service. And then once that is done, we can start replicating the repositories that we're interested in. In this case, we're going to replicate software easy.io as a repository. And we're going to do this through the sync server that Easy provides, which is this host name right here. We'll specify which directory to use for the public key. That's the key there that we used here on top. And then we run a CVM-FS server add replica command, which is instant. It just sets up some configuration and registers this repository essentially that it wants to replicate this. This is very quick. And then the bulk of the work is actually done at the end when we create the initial snapshot or the initial synchronization of this replica with the CVM-FS snapshot command for the software-easy.io repository. Now, this initial snapshot will take several hours, so of course we're not going to wait for this, but I will start setting it up and see what happens. Okay, so let's go ahead and do that. I'll start with creating this directory. Then we need to grab, I think I copied it right here, downloads, easy.io.pub. So you need to grab the public key for easy.io. You can find this in several places. For example, on GitHub and the easy.io, on the easy file system layer repository, it's available there, although what hidden in a YAML file. You can also grab it from the CVM-FS config repository, or if you just want to download it as a file, you can go to the repository here, the config repo repository in CVM-FS contrib. You go to the default branch, and you navigate to the keys that it has for easy.io. You can actually grab that file right here. So that's the file you need for setting up your mirror server. In this case, I already have it right here. So I'll just copy this in to CVM-FS Stratum 1. All right, so that should now be here. Now we can proceed with the second part, just copying that file into the right place, disabling the Geo API functionality so that doesn't cause any trouble. Adding the replica. So this will be almost instant because it just registers the replication as well. And then let's see what happens when we start doing the snapshot. So this is going to, ooh, that's interesting. What did I do wrong? So I added the replica. It's maybe not happy with, maybe missing this guy. Okay. Something always goes wrong when you're doing live demos. Okay, that was supposed to work, but it's actually not too bad because this snapshot step is going to take a very long time. I wanted to show you what happens when you launch it. It will start pulling in data to create that full mirror. Now, since it's going to take hours, we were not going to wait for it anyway. I actually have a prepared version of this ready to go, where the data has already been downloaded. So here, this 360 gigabytes that you need to mirror easy is already here. I still have the outputs of the command available. So this is when I was running the initial snapshot. You can see that it was downloading the different parts of easy here, making sure everything is up to date. And then in the end, it downloaded a whole bunch of data. And it says in 100 minutes here, it actually took longer. I had to restart it twice because of network trouble. But it can also resume after it has done the snapshot partially. So this will definitely take a while. In the end, you'll have a whole bunch of disk space that is used. And then you're ready to start using this as a mirror for easy, for example. So let's proceed with that. Let's see where we are here. All right, so suppose this initial snapshot worked. Like I did on the mirror server I had prepared. Then we want to make sure we're actually using it. So we'll again need to reconfigure our client for this. So I'll try that. Now, one detail here, this is actually not a recommended setup because there's no proxy involved here between our Stratum 1 and the client that we're running on. I'll fix that in the second slide after this. So what we really want to do here is make sure that the CVM-FS server URL setting that we have, that is specific to easy.io. So that goes into domain.d easy.io.local. It's using our private Stratum 1 server. So let's go back to the client configuration here on the left. And in domain.d easy.io, we'll go ahead and change this part. So out of the box, this is pointing to the two mirror servers we have in the cloud for Easy. We want to change this to use our own mirror server. This IP address, and this funny part here at the end, we need to keep. This looks a bit strange, but that's, let's say, a placeholder for CVM-FS to use the right repository. Let me make sure I didn't mess this part up. That looks okay. And of course, I didn't open this with sudo, so we'll have to redo it. We're changing a system-wide configuration file, so we can just do that. All right. So we change the configuration, and we need to do a reload of our config. And then we should still be able to access Software Easy IO, which it doesn't. Sometimes you need to trigger a remount for that, and the demos are going fantastic. Of course they are. So this looks okay. Maybe because of that proxy. Yeah, let's disable the proxy. That's probably the issue. Load again. So our proxy is not configured yet to use our private Stratum 1. There we go. Okay. So now that's working again, and I can show you that it's really using our private proxy here. So it shows us the IP address of our private Stratum 1, and it also says proxy direct, which essentially means there's no proxy being used here yet. So that was my goal, at least for this part. We're directly connecting our client to our private Stratum 1. Now, if it's only one client, again, that's fine. If it's a dozen or so clients, that's also okay. But if we're connecting a whole cluster to this private Stratum 1, we need to be a bit more careful and put one proxy or maybe a couple of proxies in between to offload that private Stratum 1 bit. So that's our next step. We'll reconfigure the proxy that we have to also proxy for our private Stratum 1 server. Now, that's not too complicated. If we go to our proxy here, we just need to edit our configuration again, make sure that the IP address of our private Stratum 1 is listed in the ACL, the network ACL. So the proxy can also proxy for that particular server. I'll need to reload the squid configuration after doing that. Okay, and now we can go back to our client here on the left. And put back our proxy. So the proxy IP address hasn't changed, just its configuration has changed. So we put that proxy back in place. We reload our configuration again. We check it's still working. And if we do the stat -v again, it will now tell us that it's using both our own private Stratum 1 and also our own proxy that we have set up before. And it says online, so that looks nice and dandy. So that's exactly the kind of setup you want or you should strive for, is where you have your private mirror server, which has a full copy of your repository, and then one or maybe a couple of proxy servers in between, which offload your Stratum 1. And then here to wrap this up with, as I showed with CVM-FS config stat -v, you can check which connection you're actually using. So you're aiming for your own Stratum 1, your own proxy, but also this shows you some information about cache usage on this client. So how much of the CernVM-FS client cache is actually being used. which revision of the repository, so which version of the CernVM-FS repository are you currently serving, and how soon will it reconsider that and ask again to the mirror server what the latest version is. And you can also see how often you're getting open calls and open dir calls for that particular client. So you can get some usage information out of this as well. All right, and then we're back to Valentin.
All right.
Alternative access mechanisms.
Yeah, thanks, Kenneth. So you saw now how to set up CVM-FS in the ideal scenario. That's a bit the cloud computing setup. So we mentioned that we have network access to our proxy and Stratum 1. We have a local disk that we can use for a cache, and we have the CVM-FS client software. So in HPC clusters, sometimes you have these can be special machines, no, and you have various constraints. We have luckily kind of a toolbox of workarounds and alternative solutions to get actually the software out of CVM-FS. And sort of there's a few solutions that I'm going to show now. They all come with trade-offs. So I think ideally the best scenario is always, if you can, go to a setup that is basically what Kenneth just showed. But if you can't, here's like a few workarounds to make CVM-FS work even on systems where you don't have all of these facilities available. So, and then first up on the next slide, if can continue, right? Thanks. So, right. So basically, the best case, as we said, we have here network access to the internet. We have a worker node with a local disk and the CVM-FS endpoint installed. On the right here, you can actually see a bit the worst case. So especially also high energy physics, they put in a lot of work to make their software work also on HPC sites that are nowadays pledged as part of the computing resources that the member states provide to CERN. And so the worst case is kind of like this worker node that doesn't really have any network connectivity and might not actually have really a local disk where you can cache stuff and is not installed. So you can see that people have built quite a complicated workflow where they actually kind of like trace, the files that are being accessed by a job on CVM-FS, and then download those and get them kind of to the node by some kind of data transfer. Right. So let's see how we can do some workarounds. The first tool that I'm going to want to show you is CVM-FS shrink wrap. This is for when you have no network connection or a client on the nodes. What this basically does is that it copies contents of the CVM-FS repo to a local file system, kind of like making its standalone packaged thing. That's why it's called a shrink wrap. Now you might ask, since CVM-FS is basically a POSIX file system, why you couldn't just rsync, for example, the files that you want out of CVM-FS and make an archive out of that. And the answer here is you can, but its shrink wrap is a bit more efficient. In particular, it keeps the deduplication so that if you have versions 0.1, 0.2, and 0.3 of a software that might share various files, you can actually then avoid copying the files that are the same, even on kind of like a sub file level. So because CVM-FS chunks the file and kind of like then even keeps the same chunks of a file that are the same deduplicated. And then you create an archive basically out of this object store that we have backing CVM-FS. A similar tool is also CVM-FS preload. This will actually preload the cache, and then you could actually transfer the whole cache directory to a worker node. The downside of all of this is, of course, that it's labor intensive, and because you really need to kind of like do this whole workflow, define what you need, and then kind of like look how you can actually deploy this to the worker nodes. All right. Next up, what if you actually have no local disk on your worker nodes? So there's a here it depends very much how your system actually look like. So if you have a shared file system that might be available, but where you don't want to where we want to avoid stressing the metadata server too much with many files, is actually a possibility to use a loopback file system for the cache. So here then you avoid putting like many small files that CVM-FS uses into this cluster file system where this might struggle then to keep this up to date. And you basically end up with one file per repository where you have it. There's a configuration that depending on the cluster file system can work quite well. This can actually be extended to use different sources for the cache. So, for example, we also support using a RAM cache, where you just create a RAM disk, and we can also do something where we mix on the different caches. So this is what we then call tiered caches, so that you have a RAM cache first with a certain size, and then it kind of can overspill into a cluster file system if that's there. I'm just mentioning that putting the CVM-FS on the client, the cache on NFS, and basically the mount point on NFS and exporting this um, is not really recommended. Sometimes is necessary, but also comes with kind of like a lot of issues and operational problems. All right, moving on. Then the final solution for a scenario when you have no admin privileges, basically. So you could basically use CVM-FS. You have a local disk where to use it, but you can't. You actually don't have the CVM-FS client installed on the worker node. So we have a tool that's mainly developed and maintained by Dave Dijkstra from Fermilab. And that lets you actually mount CVM-FS repository as an unprivileged user. Basically downloads all of the binaries and mounts CVM-FS in a folder that is not /CVM-FS, and then pulls a few tricks to make your application thinks that actually it reads from /CVM-FS. So there's in various modes, sort of the unprivileged namespace fuse mounts, it's one of those, and it can also use Aptainer to basically make use of the features of Aptainer to basically make your application see all of these mount points in /CVM-FS. The biggest downside of a setup like this is that you actually can share the cache because it's in your local directory, and basically all other jobs that are running jobs can see the cache that you have in your local directory. And this is one thing which actually makes CVM-FS efficient, is that that you have the system-wide cache where you then might actually then be able to deduplicate files as well, and you already have everything that the job needs in the cache. So here actually Kenneth will show you this live and in action and do a quick demo with CVM-FS exec. So back to Kenneth.
Yeah, indeed. Yeah, I think this is a very useful tool because, as Valentin mentioned, you don't need any special permissions to run this. So as long as you have an account on a Linux system somewhere where you can create some files and yeah, run some small commands to compile something or to set up the CVM-FS exec tool, you can actually get access to repositories pretty easily. So let's do a quick demo of that on a system where it makes sense, at least to me. So let's make this a bit bigger. We'll log in here to one of the Euro HPC systems, Meluxina in Luxembourg, to the login nodes where they have a bit of a particular setup. There's no module command available here on the login nodes because they want to discourage people from running software directly on the login nodes, which makes a lot of sense. But it is a bit unfortunate because I cannot even run any very simple test commands or do some kind of sanity check of my job script before submitting it, which is a bit annoying. Now, there is an easy way to get access to Easy here, so they don't have CVM-FS on their login nodes either installed. But through CVM-FS exec, I can actually solve that myself without really asking the administrators and without doing anything that I'm not allowed to do. So to start with, you clone the CVM-FS exec repository from GitHub. You go into this directory, and this has a make dist script, which you need to run with. I forgot what the default stands for, probably like default configuration. And this will actually download the CVM-FS RPM, unpack it, and then do some magic to it here in this dist directory. So this is really an unpacked version of CVM-FS. And that's actually sufficient to then also run this binary here, which uses CVM-FS, tell it which repository I want to use, and here, for example, start an interactive session with this repository mounted. So let me show you, before I run this, if I run CVM-FS, or if I poke the repository, it's not there because CVM-FS is not installed here at all. I run the CVM-FS exec command to start a new interactive shell in an environment where it is available. I can show that it is really available, and not only that, I can source the init script, which says we're on an AMD Rome system here. I can load a GROMAX module, so now I actually have the module command available because LMOD is part of the easy compatibility layer, and I can run the GROMAX binary as well. And again, here it's transparent. Actually, CVM-FS is downloading that binary for me and those libraries, but now I actually have software that I can start running without too much effort. Now, for single node use, like Valentin said, this is good enough. For multi-node use, you can also make things work, but you have to be very careful. If multiple servers, multiple nodes start using this tool together, you have to make sure they don't step on each other's toes in terms of managing the cache. So with a bit of tricks and being careful of where things are located, you can actually run multi-node workloads with this as well, but it gets hairy very fast. So it is not really a very good experience. So it does come with some downsides, but it does work. Okay, back to Valentin.
Right. So now we want to quickly talk a bit about monitoring CVM-FS. So I think that monitoring is an excellent tool to ensure that the system is running smoothly, and that actually lets you also tweak the performance quite significantly. So one particular specialty about CVM-FS is not that we can't directly give you feedback from when you do a file system access, as it's kind of like a file system. And then we also talk a bit about this in the next session, which is troubleshooting. As it happened before, you saw that you kind of like get an LS, an IO error, but how to interpret this, we talk about in the next section. So one important source then for monitoring is definitely the syslog and different health checks that CVM-FS provides. And then in one particular, we have quite a bit of performance counters and various other data. So if you're interested in really looking into the internals of CVM-FS, we're here for you and expose quite a bit of information that can be monitored. I would just want to highlight in particular one important piece of information, that is the frequency of cache cleanups. So we have a cache now that is cleaned up frequently, and when it gets full. And actually, people often ask us for recommendations about the cache size and the cache configuration. And oftentimes, the best way to figure this out is actually to just look at how many times your cache gets cleaned up in the last 24 hours. And if that is really frequent, like much more than the length of a typical job, then probably the cache is actually too small. And the way that you can access this information and a lot of other information is actually this CVM-FS talk command. What this does is it talks through a socket to the running CVM-FS process and lets you get various pieces of data and communication from there. So I think that that you saw previously, and there's a lot of other things that you can actually do with CVM-FS talk. And in particular, I think if you're only going to look at one quantity, I think this number of cleanups is an important one. Another one that can be very quite interesting is to look at the current revision that the client sees. So basically, we that's a bit the versioning of our software repositories. And if this version number is differs from the one that you actually have on your Stratum 0, where you just published a new software version, there might be some network issues. Sort of this is the likely explanation for something like this. So it's always good to monitor this to see the possible issues. All right. And to the next slide, just want to point out. So we as the development team usually don't actually run the monitoring or the deployment, for example, for CERN, but we do actually have we do provide, at least we try to collect various solutions that the community uses and that can be helpful then to share and to have in a repository. So for example, there's a collect-d plugin that is used by our colleagues from CERN IT that is, I think, quite nice. That is available under the URL from our GitHub organization. There is a server monitoring API that it can actually help you. I think this is most interesting actually if you have different organizations running running the same Stratum ones, no, and you want to kind of like organize and monitor to see the overall health of the whole infrastructure. Sort of then this becomes very interesting. We have a few things that are already built into CVM-FS. If you install it, you get this check CVM-FS script. This is basically intended for use with Nagios, but it's a basic bash script. So this is also something that gives a nice health check for CVM-FS, and this we recommend to run on worker nodes just to be able to be confident that CVM-FS is working. And what I have as well is if you have an influx database set up, there's a variety of these performance counters where you can configure CVM-FS to send them to an influx DB. And there's more information about this in the documentation here. All right, and with this, I think we can actually show you now the production dashboard from CERN IT. And I'm going to hand over to my colleague George, who's going to screen share and show you quickly what that can look like for the Stratum 0 and Stratum 1 at CERN.
Yes, so I guess you can see my monitor, right?
Yes.
Okay, awesome. So here we have an overview of what's happening on the Stratum 0. We can see here the disk requirements we have. Right now we've passed the orders of the 1 petabyte. Let's solution of
so here we're
disk
quite a
users,
bit bigger than
we are in the order of petabytes. At the moment there are 70.
There's a bit of lag with George's, I think, in terms of sound. But I don't know, Valentin, if you can explain what we're looking at.
Sure. Okay. No worries. So the top plot here is actually the same one that Kenneth showed before for easy. So this is really the disk that is required to store all of the CERN repositories. And here you can see this is 70 repos, 23 billion files. This is the number that I've mentioned before. Although this is before deduplication. And you can see here that we're about 1 petabyte just for storage that is used for the software of all of the repositories at CERN. So that is quite big. So it can scale quite to large numbers. What you can see as well here is kind of like these small these small bumps, no, where basically the repository grows, and then gets down a bit. This is our garbage collection at work. So that there's a bunch of nightly repositories where actually people build do a nightly build of the software, publish this to CVM-FS, do some tests with it, and then after a while it gets deleted again. And then what typically our repositories can do is to run garbage collection, and this basically then removes actually again these things. So we still have a certain growth because the non-nightly repositories will basically keep all of the software, but this is basically this. Yeah, an interesting metric here as well is kind of like the root catalog size. Sort of this is the metadata for the repository. It's interesting to measure. This is kind of like then one of the things one can tweak by introducing nested catalogs. I think actually the biggest tier, we only just realized that I think they didn't have the repository set up in the ideal way. So that is something that, but then one can also monitor. Then again, we have this, basically the same numbers again per repository, so there's quite a bit of information here as well. It's interesting to see actually that the biggest repository here is our container repository, so that's still quite popular. And then actually the real experiment repositories are still an order of magnitude smaller for all of this. What is monitored here as well is the whitelist validity. Sort of this is connected to our cryptographic verification that actually the software that you access is the same one that is on the Stratum 0. And here there's a mechanism where you actually have to re-sign the whitelist. Usually this is done automatically, but here is also good practice to monitor this, to see that actually the repository has this valid whitelist. And then there's still like a few network access plots, which I think is they don't give too much information here. So that's basically then shows the activity of publications for this. Sort of this is kind of like can give you a bit of the idea about the CERN stratum 0 and 1 in numbers. And here we have as well, monitoring for actually the squid proxies. So this is what Kenneth also set up just before. And here you can see that also the CVM-FS deployment is quite busy. Basically, they really get hammered. They have a quite high hit rate for like a high rate of requests, but they also get a decent hit rate. Sort of there's basically this shows the cache hits and cache misses of the squid. And I think that is also quite interesting. And sort of these are some of the things where we can also do some monitoring on the proxies, just as kind of like an inspiration, maybe. All right.
Yeah. Okay, I'll take back the screen share. Like this. Okay, you should be seeing the slides again. So we can continue. We're done with this part, right, Valentin? Yep. Okay. Yeah, back to you for the troubleshooting.
Right. Okay. Now is the troubleshooting. So you saw before that sometimes things can go wrong, even though I think we try to make this as robust as possible. If you go to the next slide, there's a couple of tools that we have and that are good to know about that you can use to debug issues. So some of the commands that you might have already seen is the CVM-FS config that lets you do various things, sort of reloading the config, showing the actual configuration. Then CVM-FS talk, which gives you information about the state of the currently running system, and then this config probe, which also does kind of like a very basic check, health check for CVM-FS. If for connectivity issues, it can actually be very interesting to just basically take a look at the URL that is being used, and then do straight up standard tools to access actually the repositories. So since it's all plain HTTP, in principle, you can always use the server URL and do a curl on the server URL to get basically the manifest of a repository. And this is the best way to actually see if there's a network problem or is actually the client that has issues. For mounting, sometimes the issues with AutoFS. And it can be interesting to just basically disable AutoFS and try to mount manually to check if that actually is the issues. Oftentimes, the insufficient resource. A typical culprit here is the disk space that is used for the cache, but also the network and the memory can sometimes make troubles here. And also, good monitoring should be able to give you more information here. CVMFS config also has a wipe cache command that lets you then remove all of the cache if it's there. And as we said before, as a file system, we can't actually print custom messages if you just do an ls on CVMFS. So actually, the detailed error messages have to go into the syslog that is usually on varlog messages, depending on your system. There's also the possibility, just to mention, that there's a log buffer attribute in the extended attributes of the CVMFS mount point that can be accessed without admin rights. So this is sometimes a very useful way of getting a quick look at the system log for CVMFS without having to have admin rights to actually look in varlog. And so because we can't really print detailed messages if you just have an application that accesses CVMFS, I'm trying to give like a short guide to interpreting error messages that you might see. So sometimes these can be a bit misleading and hard to interpret, unfortunately. The first one that you might see is too many levels of symbolic links. This isn't actually really the case that there are too many levels of symbolic links. What usually happens here that you attempt to access a mount point in a namespace that's not shared. This is often the setup that you have a container and that you bind mount the CVMFS directory. This is kind of like the standard recommended way also of using CVMFS inside a container. But then if you don't actually add this shared option, you can run into this issue. It's a bit tricky because it usually happens if you actually do the bind mount and only then afterwards you mount the CVMFS a repository here, then you can get into this into this issue. Depends a bit on your setup, but that's then there's something to look out for. Then it can happen that you see no such file or directory on a path that you'd expect to be there. So you do ls/cvmfs/software.easy.io and you don't see anything, or there's no such file or directory. So then one thing to keep in mind here is that actually we also need to download and store our metadata. This is what in CVMFS we call catalogs. And if we can't we have some kind of issue to download and store these catalogs, we basically also can't provide you with a directory listing. So this is then always good to check in the syslog if maybe there's an issue with the cache or the network. As we saw before, basically the same issue that Kenneth got. So he was trying to access the directory, but in this case it was the network the problem. No, the proxy wasn't set up to talk to the Stratum 1 that we were accessing, and so you basically just got this no such file or directory. I think in the syslog you would have seen probably also a detailed explanation that you were trying to access the catalog, but it couldn't be found. Okay, going to the next slide. Here are two more special messages that you might get on the command line from an application that is using /CVMFS. First one is very rare. This is software caused connection abort, which actually means that the fuse connection has been cut by the kernel. There's a fuse kernel module and the fuse client module, which is our CVMFS2 process. And you can actually, as a last resort, tell the kernel to cut this fuse file system. Usually this only happens when actually an admin intervenes and does this, and then you actually need to remount the repository. Sort of there's no way to recover from this. You actually need to remount CVM-FS. A very similar error message is transport endpoint is not connected. What this translates to is that again the fuse connection is bad, but this time on the user space side, sort of the CVM-FS2 process somehow has died, and it's no longer there. So it's basically there's been some kind of crash. Typically, we have a feature in CVM-FS that we automatically unmount and remount the repository, at least unmount the repository so that the exit after the crash is clean. And this is a separate watchdog process. So this you will also see if you do a PS on your system with a CVM-FS client. It usually shows you two processes for the same mount point, and one of those is this watchdog process that tries to do this automatically. In this scenario, this one also crashed. This can happen with if you run out of disk and in various other scenarios. Sort of this is good to know. Basically, what you then need to do here is to do an unmount on the mount point and then remount the repository as well. Okay. Sort of with this information on troubleshooting, I'll give this back to Kenneth to talk a bit about what to do if you want to actually create your own, say, CVM-FS repository.
Yes, okay. This will be very basic, but just to give you a feeling what that would involve. So really starting from zero and building up your own repository. This could be interesting to, for example, host your software stack, your central software stack that's specific to your HPC cluster, host it in a local CernVM-FS repository and only distribute it within your own system, or to build software on top of other repositories like Easy, for example. Now, it's not because you're building on top of Easy that you need to put it in CernVM-FS, but since you have CernVM-FS anyway, you might as well use the same mechanism to also distribute builds on top of Easy, for example. And towards the end, we'll see why that's actually makes a lot of sense. Now, suppose you want to do this, you want to set up your own host and set up your own CernVM-FS repository. That means you'll have to set up the central server that hosts that repository. So the Stratum 0 server, you'll have to set up yourself. You'll also need to make sure that you have a mirror server that replicates that repository. You don't want to connect your clients directly to your Stratum 0 server. That's not, at least from a security point of view, also from load, to avoid any load issues, that's not a wise thing to do. And likewise, for your proxy configurations, you want to make sure that they are able to also mirror for your repository, although I don't think you really need to update much there. It's mostly about the mirror servers, making sure they are replicating your repository. Not only that, of course, you'll need to make sure that your clients are actually aware of your repository. So that same public key, for example, that is used for signing the repository contents needs to be known to the clients. And if you're using additional mirror servers or separate mirror servers, you have to make sure the clients are aware of those as well. So that's in terms of setup. Of course, when you host your own repository, you want to add software to it, add contents to it. So you'll have to do that through the publication mechanism, which I'll briefly show in the next slide. And of course, you want to make sure that your mirror servers are also synchronizing regularly with your Stratum 0 server. So you need to essentially get the word out there that you have your own repository, either within your own network or globally if you're interested in making the contents available worldwide. There's links with more details. I won't go into too much detail here, but I do want to give a high-level overview what that means. So once you have a Stratum 0 server, a central server, you want to create the repository. So here I'm using the example.somedomain.some top-level domain like .io or .eu, whatever you want to use. So this is essentially the name of your repository. And actually the domain part you can pick freely. So it doesn't really need to correspond to an actual domain that is registered. It's just a name. And there's a bit of name spacing going on, but it's not really tied to specific domains. Once the repository has been created, you can publish contents in it. But this is not done by just copying files somewhere. You actually have to start a transaction for doing that. So you run the CVM-FS server transaction command. After that is done, you have an active transaction, open transaction. You can make any changes to the repository, either by manually installing software in there or by unpacking tarballs, where you have everything prepared already. And once that is done and you run CVM-FS server publish, the transaction is wrapped up and a new publication is made, a new revision of the repository is published. And with publishing means, that all the changes are recorded. CVM-FS does what is necessary to put that into its storage, let's say, and then eventually the mirror servers will pick up on it when they do an updated snapshot. They will pick up on the new revision and pull in the necessary changes. If you're talking large repositories, so say hundreds of gigabytes, I guess from that point onwards, you need to really pay close attention. Maybe you want to have nested catalogs, as Valentin mentioned when we're going through the dashboard. If things get really big, maybe you need to start splitting it up a bit in terms of metadata in the catalogs. Maybe you'll have to do garbage collection if you add and remove software installations all the time. You want to make sure that you have a garbage collection running regularly and so on. So there's a bit of housekeeping that is involved with hosting your own repository. And that was very quick. But if there are any specific questions on that, reach out to the CVM-FS community through the forum they have or through the Mattermost setup they have, if there's any questions there. And definitely check the documentation. Now, to wrap things up with, I want to briefly talk about startup performance. So some benchmarks that we've done a while ago already, which are still relevant and which are still getting the main points across. So what I really want to show here is that CernVM-FS was designed for hosting software installations specifically, which come with specific aspects like lots of small files, specific ways of accessing, so access patterns that come with it. And CernVM-FS is really tuned to support this use case particularly well. Now, that said, it's not only suitable for software installations. There are CernVM-FS users out there which really have large repositories of pure data files, which they distribute with CernVM-FS as well. So it is possible, but there is a different use case, and you maybe have to be doing some custom tuning in terms of repository settings and configuration to make sure that works well. So it's really designed for software installations, and you can really tell that that's the case if you start doing some benchmarking in terms of startup performance of software. So how long does it take until software actually starts running and starts doing what it should be doing? And especially when you compare this with other parallel file systems like GPFS or Lustre, you can really see why things are much better with CernVM-FS. So let's try and get a feel of that. And a good workload we've discovered for this is actually TensorFlow. So the startup performance of TensorFlow, where we just do an import TensorFlow, so importing the Python package, is all we really do. So that's not supposed to be doing much. It's just preparing everything to make sure that subsequent imports are actually working, or that you can start running code, Python code from TensorFlow. So that should be very lightweight. But in the background, to complete this import, you actually need 3,500 files and about 1.1 gigabytes of data. So if you count all the parts of software, shared libraries, binaries, Python files, everything combined, so everything that needs to be read to really complete this action boils down to about 1.1 gigabytes of data and 3,500 files. So that's a reasonable workload to evaluate startup performance. And we've looked at some numbers for this. So this was all single client actually, but you can already see some interesting things popping up. So to start with, and to have a point of reference, we'll start with an unrealistic scenario actually, which is where we install the full software stack. So that includes TensorFlow, but all the dependencies it has, and even down to the glibc it has. So everything, the glibc, it uses everything that is that consists of the software stack that is being used is installed either on local disk or on RAM disk. Now, this is not realistic because, okay, local disk, things like glibc usually are on local disk. But if you have a sizable software stack in your HPC cluster, it typically doesn't fit local disk anymore. We're talking hundreds of gigabytes of software installations that you typically can't or don't want to fit on a local disk and then replicate across your whole cluster on all the nodes. So you typically use a parallel file system for this. But to have a point of reference, let's see how we're doing here. So if the full software stack is installed in RAM disk, and we start from a clean slate, let's say, so the import TensorFlow has not been done yet on the system recently, we see a time of about 2 seconds that is necessary to complete that import. If we do the same thing when the whole software stack is installed on a local disk, an SSD, so a non-spinning local disk, then we see it already increases to about 4.5 seconds in the cold case. So when this hasn't been done recently and nothing is being cached yet. So that already shows there's a big difference between RAM disk and even a local SSD. Now, of course, if this has been done recently, so say you do it hundreds of times in a row, and you see how long it takes in the end, you should see something that's very close to the optimal case, because then everything is being cached in the kernel file system cache, and you basically see again 2 seconds, regardless of whether the software is in RAM disk or on the local SSD, because everything is cached in memory already. So then it feels very fast. So this is like the optimal thing we can get. About 2 seconds, we cannot really get much faster than that. So keep this in mind, the 2 seconds is like the absolute fastest. If we then start looking at more typical setups, say an NFS file system where the whole software stack is hosted, this is maybe also a bit of an unrealistic scenario. So I did this a while ago on one of our systems in Ghent, where that NFS file system was not really used a lot. It was only used by one small cluster, which was about to die. So it didn't really get a lot of activity. But you can see that the numbers here are already significantly bigger. So we're talking 6 to 7 seconds to complete that import TensorFlow in the cold situation. So when there's no cache warm-up being done. And after that has been done once or a couple of times, you see it drops to about 4 seconds, but it doesn't really get faster than that. So that's already twice as slow as the RAM disk situation or with the local SSD. So because NFS in between, you have a significant delay. It takes about twice as long. Now, this is still okay, relatively okay, but yeah, if the NFS server gets more loaded, many of us know that that's going to be a real problem, and these numbers will spike for definitely in a real world scenario. But also, if we look at more capable parallel file systems like GPFS or Lustre, we'll see a lot bigger numbers. So these are both taken also from systems in Ghent, and I had to double check this with our storage experts in our team to make sure I wasn't doing anything funny here. We're seeing times to complete the import TensorFlow of half a minute up to even a minute to complete that silly workload. In the cold case, so when the GPFS page pool cache is cold, so none of the data is actually in there, it goes more towards a minute. If it's hot caches, so if the page pool cache is fully preloaded essentially already, it still takes about half a minute because GPFS is in between. There's only one case where it was significantly better. This is when all the data is hosted on SSDs, but that's quite expensive to do for a full parallel file system. But then it's definitely a lot better. So if you are putting your software in GPFS or Lustre, at least do it on a Scratch file system. I only have the plot here for GPFS, not for Lustre, but you can find the statistics in the performance part of the tutorial on our website. So yeah, that is pretty bad. Now, the main reason for this is that these GPFS file systems are not tuned for the typical access patterns you see with software. So lots of small files is not a good access pattern for GPFS. It doesn't really like that, or it's not particularly tuned to like that typically. You can definitely tune your GPFS file system so it does a lot better here, but in general, that's not what people do to host software on. It's really used for large data files and a totally different access pattern. Now, if we look at CernVM-FS, so let's start with the cold case where the CVMFS client caches are empty essentially, and where no activity has been done recently. If we do this and we have a private proxy within our network, which does have the data already, then we can see that we're below 10 seconds. So that's already a lot better than we see with GPFS and Lustre. Also, if we don't have a proxy and only a local mirror server, then it's a little bit longer, but it's still quite good, assuming that certain one mirror server is quite close to our nodes. If we rely on public mirror servers, which are in the cloud somewhere, which may be very distant away from us. So in this case, the green part here is, let's say, going towards 50-ish seconds. That was still okay-ish because this is a mirror server located in Dublin, and I was running the test in Ghent in Belgium. So that's still relatively close, but you see that we're being exposed here to the network latency and bandwidth issues. And if we force CVM-FS to use a mirror server that's located in the US, then of course we're talking minutes of a wait time until that import TensorFlow completes. Now this is in a cold cache scenario, which is the absolute worst case scenario. That's where CernVM-FS has to download all the data before it can complete the request. But that's also not really a realistic case. At least some parts of the software you need will probably be already cached closer to you, either in your proxy server or on local disk of the client. If we look in a more hot scenario or warm scenario, so hot cache, this is really our reference point. Again, everything is hot in the kernel file system cache, so all the data is already fully cached in memory. That were very close to 2 seconds. But you can also see if we only warm up the CernVM-FS client cache, that we're still below 6 seconds essentially, even if our Stratum 1 servers are very close away. We still do very well. So there's not a lot of overhead, at least when the biggest part of the data that you need is already cached. And this is really the ideal scenario where everything is cached. But if you're somewhere in the middle between a cold and a hot scenario, where at least some parts of your software are being cached close, especially if you have a close proxy server or a close mirror server, you're getting very good startup performance. So this really reflects that CernVM-FS is really tuned for hosting software installations, and that you're probably going to have a better experience than you have with putting your software on GPFS or a Lustre or even an NFS file system. Okay, and that basically wraps up our webinar. So just some acknowledgements, thanking Valentin and his team members, Laura, Georgios, and Jakob, to help out with preparing the tutorial, and especially Valentin for doing the presentation as well. And then also Thomas and Bob, who gave some feedback on the contents of the tutorial within the EASY project and within the multi-scale project, which is currently funding the efforts towards EASY. We have a whole bunch of links for more information, documentation for CernVM-FS, but also GitHub, the forum, and the Mattermost channel they have for reaching out to the community. Likewise, for EASY, you can find us on GitHub and Slack. We have a YouTube channel where this webinar will be posted as well. And we actually have a support portal as well, where you can ask questions or get help if needed. And then similar for multi-scale website, YouTube, and so on. That's all we have for the webinar today. I think we still have, let's say, 10 minutes for questions. I haven't been keeping an eye on the Slack, but if anyone wants to raise a question here, please raise your hand in Zoom and we can let you unmute yourself to get those questions answered. And of course, you can always ask additional questions in Slack as well. Valentin is around there as well, so am I, and so are many other people who are familiar with CernVM-FS. So I see Kaspar has a question. Go ahead, Kaspar.
Yes, can you hear me?
Yep.
So I actually have a couple of questions, so let's see how many we do. And first, I have an addition to Kenneth's performance data, because we actually, at CERF, we set up a private Stratum 1 on our HPC cluster, and we did some scaling tests to try and stress test that private Stratum 1. We went up to 96,000 ranks on 500 nodes and trying the same routine that Kenneth did, so importing TensorFlow. And basically, we saw that on a cold cache, the fastest process was done within 35 seconds. The slowest one took 1 minute and 14 seconds, which was way better than the TensorFlow that was hosted on our GPFS file system. So there, the slowest one took 2.5 minutes. I wasn't in control of the GPFS cache, so I'm not sure if that was warm or cold. But at least for us, that was a very good indication that using CVM-FS for the software within our system is a sensible choice. Having said that, I'm also interested in Valentin's opinion on basically, if you have a Stratum 1 already in your system, what is the value to then also put a proxy in between? Because, well, basically with the stress test, I saw that for performance, for now, it seems fine. Now, there's not a ton of users using this yet, right? It was just me trying a single software, so probably that was cached on the server side as well. But yeah, just curious about your opinion on having proxies in between there.
Yeah, it's a good question. I think if you have a really a private Stratum 1, that can work quite well for some time. I think the idea in the end is to free up the Stratum 1 for several of these tasks that can take longer as the repository grows. These are in particular doing the snapshots, doing the garbage collection, and these other things. And you might actually, like, we usually don't have private Stratum 1 at all of the basically the data centers. So that then typically you have kind of like a regional Stratum 1, and then really kind of like a proxy that is closer to the data center. If you then actually run the whole Stratum 1, in principle it's a similar thing. It might still help you kind of like to get load of the Stratum 1. So but it's very possible also to then add a proxy as if you see that actually your Stratum 1 then cannot keep up with doing snapshots and serving data, and you're getting worse performance from that.
Okay, good to know. Thanks.
I think there's a bit of a rule of thumb there that, let's say, for about 500 nodes per proxy or per Stratum 1 is okay. If you go beyond that, and assuming they're all actively using CernVM-FS, then you maybe need to look into additional proxies in between that. And maybe also in terms of maintenance, it's a good idea to put the proxy in front of your Stratum 1 server, maybe two, because then you can always update something without affecting production, let's say. So you could do updates in production without really affecting anything that's relying on those repositories, if you're careful enough. Okay, I think Caspar had multiple questions, or?
Yeah, but let's see if there are other questions first. Otherwise, we can loop back.
Well, I don't see anyone else raising their hand, so if you have another question, you can go ahead, I think.
Yeah, this is more about the setup that you mentioned, like specifically for HPC systems where you don't always have a local disk and you have a network file system. You mentioned the possibility of using that loopback file system. If I look at our current configuration, I see that it puts the cache, if I understand it correctly, in /var/lib, which for us is actually a file system in RAM, right? We don't have local disks. So that made me wonder, because you also mentioned like, hey, we have specific options to put the cache in RAM. Like, does that do anything differently then, or am I basically already using that?
No, I think you're basically already using this. If you have a RAM disk, that's pretty much the same thing.
Okay.
I think our the specific RAM cache that is mostly interesting then if you want to have this tiered setup, so that you have a like a very small cache in RAM and then additional cache on a local disk. So
right. Okay.
I think I'd have to look it up though, what exactly our RAM cache does for you. So I'll get back to you and look it up.
And I was also thinking about like, what is still the advantage, or is there still an advantage of having a cache in a loopback file system on GPFS if we already have sort of this local Stratum 1, right? Because in both cases, it's going to be served, it's either be coming from our GPFS file server over the local network, or from our private Stratum 1 over the local network. I don't personally think there would be a benefit of then still having a cache on the GPFS file system. But I don't know if you feel the same.
But isn't it the requirement for CernVM-FS to have a place to put the cache?
Oh well, but it will, right, on the local file system. So in var/lib, it will still put stuff there, but that might be rather small.
Yeah. So to answer Kenneth's questions, yes, and at the moment you pretty much need somewhere to have, at least for the catalogs. Basically, these are our metadata. There is a streaming cache mode for CVM-FS that will then basically skip the cache for all data files, sort of the files that are read for the software. And that can be directly downloaded and used by the application without actually them being stored on cache, which, of course, you might re-download things quite a bit. But I think that in the end, I agree with you, Casper, that I think in this kind of setup, likely the performance is good enough. It can then depend if you get if you get to software stacks that are very big, then maybe in which where maybe the cache on your RAM blows up and this is not big enough, maybe then it could give some benefits. But
Right.
I'm also not quite sure.
Mhm.
There is another question as well,
Perfect.
Caspar. So yeah, from Vasilis, he's not able to ask it himself, but let me just read it. I wanted a specific software version, and this was only available through Easy Build and Easy Extend, not available through the Easy default module. So it's basically building stuff on top of Easy. Does this protocol work in the Aptainer container mode? I was able to install it only by using Easy Build and not with Easy Extend. Also, I wasn't able to install Easy in the university SPC server, so I used the container. Is it possible to access the Easy through Slurp options and for multiple nodes, load the required module? Okay, that's more like 3 questions. They're also quite specific to Easy, I think, not really specific to CernVM-FS. So maybe Vasilis, it's better to ask this question in the Easy Slack and try to get an answer for it there. It's a little bit out of scope for this session. And we'll have to counter with additional questions to better understand the context anyway. So I think it's better if you either go through Slack or through the support channel that we have for Easy and raise your question there. Okay. Yeah, and Vasilis says thank you. All right, so it looks like he's okay with that. No more raised hands. So Caspar, if you still have another one.
I still had another one. I was wondering about transactions. So if you do a transaction on the stratum 0, and let's say you're publishing, I don't know, 5 new files, is that an atomic operation? So do all 5 new files appear at the same time? And if so, does that sort of atomic behavior propagate through the whole stack? So is it also atomic on the stratum 1s and on the client side?
Effectively, yes. So basically, I mean, the transaction, it's a bit special with CVM-FS as the data is stored in an object store. And so if you basically rename files, you're never actually going to change the data that's in your repository, but you are going to change the metadata. And this is basically an atomic operation. Basically, what we do is that we like we switch out the root file catalog that we call it. Basically, this is the main catalog that tells CVM-FS which files are in your repository, and that has basically pointers to all of the nested catalogs, and this basically defines the whole content of the repository. So what happens when you do a transaction is basically that you publish a new manifest. That's what we call it. That's the file .cvmfs published on your CVM-FS server, and that has the pointer to the root file catalog. And kind of like once that changes, basically the repository information is atomically updated.
So even a client that holds a cache, like for every operation, it will always check if this root catalog is still the same.
No, so there's various cases, and I think this can also be configured. So, but in principle, you always have some kind of delay between publishing a new root file catalog and that actually appearing. So what we try to ensure is that you know that once the client sees the new root file catalog, everything is consistent, that the whole repository is updated to the new state. And there's no inconsistent files where you have one file that's still from the old revision and one file that's already from the new revision.
Right. So for a single client, that will be atomic, but with multiple clients, I guess I could still see different versions, right? So if I do like a multi-node job.
Right. Yeah. So that indeed. And I think what for example, if you have a job that really depends on an update where you do a new transaction and you have where you push a new software version and you have a job that needs it, sometimes people actually do a check for the revision that they kind of like say in a pilot job that they checked if the revision is greater than the one that they need and that just like this it's being run. So this is one way that you can actually make sure that a transaction is there when you run the job.
Okay. Yep. Just as an idea, I don't know how many other HPC people are in the call, but I can imagine maybe checking something like this in the prologue of a job script, like just make sure that all of the nodes that are allocated to a job are on the same revision as a kind of
That's probably a wise thing to do. Yeah. Okay. Yeah, I think we're at the end actually of the webinar. So let's wrap up the Q&A. Let me flash back to that last slide we have. So we have 3 more webinars coming up in this series about different aspects of Easy. The next one will be next Monday with an introduction to Easy Build, where we'll also cover some aspects of the new Easy Build 5.0 version. And we'll also look into using Easy Build on top of Easy a bit. So we're always making a connection to Easy in some sense. All right, thank you very much for attending. We'll wrap up here. If there's any more questions, please go through either the Easy Slack or if they're specific to CernVM-FS through the dedicated channels there. Thank you very much.
All right, thanks everyone, and we'll talk to you there.